So what we in essence have here is that this, or this right here, is constant for whatever reference frame. So this is an invariant. So we have two invariants here. The speed of light is invariant to all reference frames, and this difference between c squared t squared minus x squared is also the same for every reference frame. And that's about it. That's about the same for everybody. Notice one of the things here is that h, we talked about length contraction here. H does not vary with speed because the speed is perpendicular to it. It's only speed that's parallel to the motion that undergoes the length contraction. Questions before we get into deriving the Lorentz transformations? Let's make sure I use the same lettering I did before.
What is that supposed to be? I made it V here. Hold on.
Okay. All right. So this basically this S and S prime are reference frames. So you can think about this as you're driving in a car and the earth is rotating while you're driving on the earth. And so S might be the earth and S prime might be your car. Because from your point of view, if you're in the car frame, you're not moving at all. The earth's moving back this way if I'm going this direction. From their point of view, the car's going that way.
Now that makes sense. Yeah, I said now that makes sense.
Okay. So I'm just parenthetically going to put in earth and car. So I can write down that the make the right positive, that the velocity of S prime with respect to S is equal to V. So it's the velocity of the first one with respect to the second one. Second one is the reference. So if I have some event happening here at this location, and if you need to, you can think of this as that this is a traffic light. I got a long line here and I got various traffic lights. And so I'm at one traffic light, there's another traffic light up ahead. So how far away it is from my point of view and how far it is away from the person in the car varies with time. So this distance here, I would label as x, and this distance here, I would label as x prime, and this distance right here is just vt. So first, let's take a look at this from the point of view of Galilean relativity. That x is equal to x prime plus vt. So the stuff that we've been basically dealing with for up until relativity, we have, that's the relationship there. In Galilean relativity, t and t prime are the same. There's no difference in time. So from this point of view, x prime is equal to x minus vt. Now we have that x squared minus c squared t squared is equal to some constant. So since that relationship there is supposed to be invariant, it should be equal to from S frame, or the S prime frame should be the same. And so if we plug, let's plug into here. So that would be, from Galilean relativity point of view, x minus vt, got my squared, minus ct squared, that's times the same. And so this is x squared minus 2x vt plus v squared t squared minus z squared t squared is equal to x squared minus c squared t squared. Questions to here? That cancels out, that cancels out, and so I'm left with, if I just bring that over, 2x vt is equal to v squared t squared. I cancel some stuff out here. Not the one I wanted. That v cancels out with one of those, that cancels out with one of those, and so I have x is equal to 1/2 vt. In essence, what I have here, if Galilean relativity had value at this point, then this distance would be basically half of that. And that's clearly not the case. So Galilean relativity is missing out on something. So that's justification for trying to come up with a set of transformations between the two reference frames. So we're going to have, there's some event that happens in some position at some time in the S frame, and then in the prime frame. So you got two sets of people moving along, not moving, or however you want to do it, on Earth or in the rocket ship, who are both looking at this and going, this happens at such and such a position at such and such a time. Now, the relationship between them, we are going to make the assumption that it is a linear relationship. And I'm not going to justify that, we're going to sort of live with that one. And I can get a darker marker than this, I hope. So there's some constant A1 and A2 that I can relate between the two, and then T prime is equal to B1x plus B2t. And we just have to figure out what those are. Now we can simplify some of this by synchronizing. So if we have some light here and the car's passing by, we'll just say when the car passes by that light, that's when we start, both of them start the stopwatch. Because they're at the exact same position at the exact same time. So at t is equal to 0, t prime equals 0, x prime equals 0, x equals 0. So all we're doing is synchronizing. So as this moves along, this is where x prime is equal to 0. And so I just want to look at some time has passed from both their points of view. So when x prime is equal to 0, that's going to be a1x plus a2t. So a1x is equal to negative A2t. X is equal to negative A2 over A1t. And, oh, I think I lost it from there. Oh. And that should also just be equal to, well, that's how far that's traveling. That's VT. So this first equation here, I have x prime is equal to A1, just factoring out x plus A2 over A1 times time, which is A1 x minus VT. So we have this relationship already between the two. We've simplified it down a little bit. Questions here? Let's go to the invariance. I know that x prime squared minus c squared t prime squared is equal to x squared minus c squared t squared. Right into my invariance. X prime is equal to a1 x minus vt squared minus c squared times my t prime, which is b1x plus b2t squared, which is equal to x squared minus c squared t squared. We go through the joy of multiplying this out, so this is a1 squared times x squared minus 2x vt plus v squared t squared minus c squared times b1 squared x squared plus 2 b1 b2 t xt plus b2 squared t squared equals x squared minus c squared t squared. A1 squared x, and then multiply this out.
Water spraying.
Oh, well, that's not good. Now it's just dripping. Take a small break here while we get this taken care of. Right near the electrical outlet too. Alright, what are the chances I'm not gonna knock this over? That's it. Find out if I remember that. I had this one. All right, small little interlude there. All right, continue on with just the absolute spectacular derivation here. A1 squared x vt plus v squared t squared a1 squared minus b1 squared c squared x squared, just distributing, minus 2b1 b2 c squared xt plus minus c squared b2 squared t squared equals x squared minus c squared t squared. So incredibly obvious at this point, right? All right, what we need to do is combine stuff. I got an x squared here, I need to figure out whether the x squared parts are over there. So I've got this, and I think that's it for the x squareds. So I get a1 squared minus b1 squared c squared times x squared. Then I want my c squared t squared pieces plus this right here. Did I lose something? Let's double check. Oh, I combined the wrong thing there. The t squared I want to combine. So I have a t squared here and a t squared here. So this becomes v squared a1 squared minus c squared b2 squared times t squared. And then everything that's left over plus negative 2a1 squared x vt. Do I want to keep t out? No, not yet. Minus 2b1 b2 c squared x t equals x squared plus c squared minus c squared t squared. What amazes me is that at this point, is there any real indication that we've made a mistake or not? And we're basically plunging into this, and it's been done before, so I'm basically definitely standing on the shoulders of giants. But the faith that you have as you start into, well, a lot of physics problems, you just have faith that you're going to end up someplace and haven't made a mistake. What relativity is telling us is that this should always be true. This left side should always be equal to the right side. Because this is invariant. This should always be true, regardless of the reference frame. And if this is always true, then this coefficient of x squared should be equal to 1. So a1 squared minus b1 squared c squared equals 1. It has to. No matter what, it always has to equal that. Because this is always true. I mean, that's always true. This right here always has to be equal to negative c squared. So v squared, a1 squared, minus c squared, b2 squared equals negative c squared. And this last little bit should always be equal to 0. So negative 2a1 squared x vt minus 2b1 b2 c squared xt equals 0. And this is a common thing in mathematics where you get two things and you basically compare coefficients. If it's always true, the coefficients always have to be equal. So for the first one, b1 squared, well, actually, let's make this slightly more interactive. What does b1 squared equal? I'm not expecting you to know that you want to solve for b1 squared, but you should be able to solve for b1 squared.
A1 squared divided by c squared.
Is it a1 squared divided by c squared?
Yes.
What happened to the 1 here?
Oh, A1 squared minus 1 divided by c squared.
Yep, there we go. And in this one, I want to solve for b2 squared. in essence, what we're doing here is, I have a B1 and a B2 here, and A1, what I'm hoping is that if I solve for B1, solve for B2, plug into here, that I can eventually solve for A1. I have three equations with our three unknowns of A1, B1, B2. So for the second one, what's B2 equal?
Is that V squared at the beginning?
It is.
Okay. V squared A1 squared plus C squared divided by C squared.
Which would become A1 squared, V squared over C squared plus 1. And then the last one, we need to get B1 and B2 isolated, but we can get rid of some stuff. Time is the same here, so I can get rid of that. X is the same, I can get rid of that. And so I'm left with B1, B2. And so B1, B2 equals
A squared divided by C squared? It's hard to tell with the.
there's a B in here also. Oh, the negative 2's would go away also. So what I'm left with here from this point, once I get rid of that stuff, is A1 squared V minus plus B1, B2 C squared equals 0.
Would be negative A1 squared V divided by C squared.